Good evening. I'm Toby K. Welcome to the second video on type flexibility. Are you ready? I can't hear you because that's how video works, but I assume you're ready. We're going to look at runtime type flexibility in this video, following on from programming time type flexibility. We'll be going through help patches. These help patches in VL.ExtendedTutorials are actually very wordy. They contain a lot more words than I'll show you here. So if you prefer to just read, you can do that without watching this video. But for people who like to learn auditorily or through videos, then watch the video and also check out the help patches for live demos. Let's briefly look at the difference again between what I'm calling programming time type flexibility, often known as compile time type flexibility, and runtime type flexibility. Programming time is things like generics and adaptive that we looked at last time that resolve completely before the program runs, therefore no cost to performance either. Runtime type flexibility brings benefits to the programmer and lets you do some things that offer new features to the end user. Because things are changing at runtime, this is going to cost a couple of CPU instructions, maybe to check the type, maybe to just do a conversion. It's not usually dramatic. We'll get to that and talk about the performance for each type when we get there. We should divide runtime type flexibility into explicit and implicit conversions. Explicit conversions include things like extremely mundane conversions you do all the time that involve nodes like to this, from this, as this, etc. Then you would also find this kind of thing, which is more the subject of today, casting. That's an explicit conversion. What makes these explicit is basically that there's a specific function doing the conversion. It's explicitly, we told it as a programmer, we wanted those converted. Then we have implicit conversions. And they're implicit because we don't specifically need to have any function there that converts it. It's automatically done by v4 or by the compiler. However, it can also be confusing. How do you even find out about these? One category of these is numeric. There's specific kinds of numeric types that will implicitly directly convert into each other. Then there's a kind of conversion called upcasting that we'll go into. In this case, this is a spread, and here this is a node that operates on a sequence, which is also known as IEnumerable. We'll get to that later, but you'll find out why those can be directly connected. Lastly, there's some v4 specific conversions, like this one is from float to GPU float, which is documented in the Stride documentation. These kind of things I won't go into today, but are hopefully documented properly in their v4 libraries, intended to create some convenience for you, hopefully with a minimum of confusion. Let's start with implicit numeric conversions. So in the C# language specification, and I'll drop a link below, it says there are certain conversions that are implicit. One of those that's extremely common is from int to float. And when we look at it here, integer 32 indeed connects directly to a float 32. And the opposite is not possible. If I go float 32 and int 32 and connect those, that's a red link. No can do. We'd have to do some kind of explicit conversion. One thing is you'll notice v4 uses slightly different naming for some of these primitive types. That's covered in the grey book, and I'll put the link in the description below as well. This is a very common implicit numeric conversion that you'll run into. There's one other one that's v4 specific, which is that booleans also automatically turn into integers, which is very handy for lots of things that take an enable that's actually an integer from 0 to 1 instead of a boolean. It automatically just works. And then, because integers turn into floats, you can actually also directly connect a float to a boolean. So that's fun. In principle, most of these conversions should perfectly retain values. So integer 32, when it implicitly converts to integer 64 can, of course, capture the entire range of integer 32. The notable exception is this one, integer 32 to float, really high integers. If we, for example, go max value integer 32 and zoom out here, you'll see, yeah, these are already not exactly the same number. If I do a minus, and we should check that turned into a minus, integer 32, 12,000 or something, connect that there and also connect an integer to it. Yeah, these are definitely not the same value. So you want to be careful of that with implicit conversions, but honestly, it rarely comes up unless you're playing amongst the really high ranges of the integer. And also the same for the negative ranges, because this is a signed integer that can go minus. Something to be aware of is that the generic functionality that we talked about last video, that's adapting the type of nodes based on their context, other types that are connected to them, might interact with implicit conversions in ways you don't expect. For example, we connect this integer and it says, the plus should be an integer. And then at the bottom, we want to connect it to a float and it says, well, integer converts to float. So I'll do a little conversion there. Then when we go to connect this, no green node says, I'm not sure those are meant to connect. Now we can force it if I hold space, or in fact, I think if I just click, don't necessarily need space, then it works out and says, you must have meant a float 32, 5 plus 0.5. So that means that implicit conversion has moved to here. This is integer to float. So just something to be aware of. What you can always do is double click on the node and it should give you the specific implementations it can do. On the performance side, implicit numeric conversions are all pretty fast, but they're not totally free. It's still going to be a couple of CPU instructions somewhere to convert these types. However, I would almost never worry about this in terms of optimization. It would be a very extreme case where I want to optimize out this type of conversion. Let's have a quick look at explicit numeric conversion as well. So this you might already be familiar with. I can put a type in the node browser and often find it has a bunch of 2, X and Y, that will allow me to do a conversion. They're pretty straightforward, these converters. Just bear in mind what they might do with an unexpected value. They almost never throw exceptions or anything like that, but it means they'll have some other overflow behavior. For example, in this case, converting to a byte, if I go negative, then it starts that byte count again from 255 down. Or if I go above 255, get a similar overflow behavior. But bear in mind, it could have done something else, like clamped to the values or something like that. So that's just something always to look at. Also like to point out that if you're converting a float to an integer, one of the most common conversions, there's more than one way to shake this sauce bottle, which is you can use the regular 2int32, which just seems to take the integer part. And there you go. But floor, which actually does the same thing, but you're specifically saying, I want you to round down. Ceil, short for ceiling, saying, I want you to round up. And then round, which does the typical mathematical rounding behavior. When you're below half, you're lower, and when you're half and above, you go higher. Good fun. Explicit conversions will use variable amounts of performance depending on the function you call. All of these numeric ones will be pretty simple. However, something like converting to or from strings will usually require a few more instructions. Next, let's do a little theory on two things called inheritance and interfaces. Both have a main use case, which is enabling different kinds of modularity in your code. Both enable shared methods. To invoke a shared method, you must use the common type. And telling the compiler to treat one type as if it's another is casting. Therefore, both inheritance and interfaces enable this thing called casting, but it's not their main use case, and that's why they're kind of different things. Let me show you what I was just talking about. So this is a case of interfaces. We've got two widgets, round widget and rect widget, and they both implement an interface called iWidget. And the reason we're doing this is because we both want them to be drawn by the same piece of code. So we want to call the same draw method for both of those. And in this case, iWidget, the interface, has a method called draw. The way we do this, we create a round widget and a rect widget, and because they both implement iWidget, they're both able to be added to a spread of iWidget. And this is casting. You see it's rect widget here, but when it's added to the spread, it's iWidget. And then we can call, this is what I mean by shared methods, we can call that iWidget.draw. So both of these are able to draw out the same pipeline. If that's not perfectly clear to you yet, that's fair enough. We're going to deep dive on all of this shortly. Interfaces, however, really deserve their own video, which hopefully I'll get around to making in the future. So we need a little background on inheritance first. So we actually can't create inheritance in v4, but it's common in external libraries, so we should still know how to identify it to use its type flexibility features. What inheritance does is it allows parent-child relationships between objects, and that's usually that children are more specialized versions of the objects. You can find inheritance in documentation. So let's look at the documentation. This is a library called SFML that I used in VL.GameAudioPlayer. It's originally a C++ library but they provide a C# binding. So this is the inheritance diagram for a class called SF Sound Source, and that class inherits from AI resource, and it has children sound, soundstream, and music. Sound source has some methods like set pitch, set volume, also getters for those, play, pause, and all of those methods are available to the children. So sound and music do some extra things, but they can all use the play and stop and so forth methods of sound source. And that's the function of inheritance, the main use case. Okay, but what if there isn't documentation with a nice little graph? What we can do, if I look in the node browser here, just for an example, there's a bunch of mouse notification related types. There's notification base and mouse horizontal wheel notification, mouse wheel notification, mouse down notification, and these actually all inherit from each other. If I look in the code, and in fact, because V4 open sourced its standard libraries, I can find the C# code, and it's here with this colon symbol that's saying mouse button notification, inherits from mouse notification. And I could trace that code with a search to find all those inheritance relationships. Hopefully we'll take a closer look in a future reactive tutorial on these actual mouse and keyboard notifications and how to use them. So interfaces, let's have a look. What's behind the IO box here? We can create interfaces in V4, unlike inheritance, although for a while the devs have been saying they might update the UI. So yeah, what you see might change in future. They really need their own video. We're only going to do a shallow dive right now. And sliding down. Oh, that's a tricky one. There we go. So what are interfaces? Interfaces are special definitions that contain signatures of methods you want to share and share between different objects. So before with inheritance, the child could only have one parent, and within interfaces, multiple objects can implement multiple interfaces and share functionality. Easier to show than tell, you'll see in a sec. Interfaces have a couple of naming conventions, ones that they start with a capital I, at least in C#. For example, iClock. Sometimes you'll see they have an adjective, usually meaning they only do one thing. For example, the interface IEnumerable is adding functionality that means collections, in this case, can be enumerated. And I bring up this one because it's an exception to the first rule. At least in V4, IEnumerable is renamed to sequence. Okay, and how do we find out about inheritance? What inherits what? I'll show you the way it's done in V4, but also we can find it in documentation of external libraries. And if not there, we can find it in code. And let's have a look at those. Let's see what it looks like when an object implements some interfaces in typical documentation. This is the documentation for the array class in C#. And you'll see here it says implements. Implements is the keyword. Objects implement interfaces. And there's a list of the interfaces it implements. In code, what this looks like is you'll see this line, which is the definition of array, and then it uses that same colon symbol and gives us a list of the interfaces. Now, if you look there, you'll see there's only 4, and if we go here, there's more. That's because there's also an inheritance thing going on in interfaces. In this case, you'll see it implements iList, and if we go into iList, we find iList implements iCollection and IEnumerable. Therefore, array implements the things that iList implements. For the way it looks inside V4 patches, let's go back up here to where we have these definitions. Round widget, rect widget that implement iWidget. iWidget, if we go inside, it's an interface as chosen here in the Process Explorer. If we go into round widget and rect widget in their Process Explorer, you'll see it has this category interfaces and iWidget is listed there. So that's how we see, should see it here too. That's how we see what interfaces are implemented in the patches. Last piece of the puzzle, how does it look in the node browser? If I go round widget, you'll see these methods belong directly to round widget, create, draw, radius, and set radius. But then there's another version of draw, and that's the version that belongs to iWidget. And so for both inheritance and interfaces, you'll see written in square brackets if a method is coming from one of those. So back to our scheduled programming of talking about type flexibility. So now we can identify what inheritance and interfaces are and the relationships. We can talk about casting, which is an important type of type flexibility. There's two kinds we need to know about, which is upcasting and downcasting. So let's see what's behind the curtain. Upcasting. This is when we go from specialized type to the more general type. Inheritance, that's going from child to parent. Interfaces, that's going from object to interface. You'll see all this in practice soon. And that's an implicit conversion. We can directly connect those. And downcasting, we go from general type to specialized type, and that's parent to child with inheritance, or with interfaces, that's when you're going from the interface back to the original object, which you rarely do, but there can be cases. This has to be an explicit conversion, e.g. using a CastAs node. And the reason is because in downcasting, there's the potential for more errors. So the compiler really wants you to confirm that you know what you're doing with some explicit casting. Let's see that all in practice with our old friends, round widget, rect widget, and I widget. Round widget, if we go inside and look at what this does, let's look at the draw operation first. It draws a circle, and it has a property radius, and it has an operation to set radius, because it's a circle. Rect widget is very similar, but it draws a rectangle, and we set size. Now, we could have a unified way to set size or radius, but for the purposes of this, let's say they're very different. Round widget needs a radius setting operation. That's the only possible way to do it. Rect widget needs a size setting operation. However, we want them to be drawn by the same pipeline. So we have iWidget, and in the interface, it actually just has an operation called draw. It doesn't need any code. It just defines literally that there's an operation called draw and that it has an output called layer, which happens to match the draw operations in both round widget and rect widget. As I say, on a future interfaces video, go into a lot more detail about that. But for now, we just need to know enough to do the casting. So on the drawing side, let's make a spread of iWidget, which actually that's just the name spread iWidget, but it will also be the type spread iWidget. Great. We want to add some stuff to this spread. So we're going to use add spread. 1, 2, and you'll see this has already been typed spread iWidget, and so item, it's expecting an iWidget. If I go round widget create, I can connect from the bottom of round widget to the input on the add, and then you'll see it's an iWidget, and already this is the upcasting. So remember I said upcasting is implicit conversion. We don't need to put any special node there. Round widget is being converted to an iWidget to join this spread. And we can do the same with rect widget. There we go. And so that's the upcasting already. Just to flesh out the use case, I'll show you now if I go for each spread iWidget, I can now use the iWidget's draw operation to get a unified draw. And if I do this layer here, I think I'll need a group spectral to see it. And it's going to draw, oh, actually nothing yet because these have neither a radius or a size. There we go. There we go. There's a rectangle and a circle both being drawn, proving it works. Okay, now let's look at a downcasting case. So first, let's put this on create so they only get created once. They're not recreated every frame. And now let's take our spread iWidget. We're going to get slice because it's a spread and index 0. So we get that first one, which should be this round widget. Then we're going to go CastAs. CastAs is the explicit conversion that's going to go, and that's in advanced. Now we want to see if the cast was successful. Now currently this is grayed out. CastAs has generic a T here, and it needs to know the type we're going to cast to in order to do anything. However, we're going to put that in an if region, and this is the point of the success, because we only want this code actually executing if the cast is successful. Making a round widget execute an operation that only rect widget can do would be an error. So let's go round widgets, unique operation, set radius. These are mutable classes, by the way, if that's not familiar to you. And now I should be able to set the radius of round widget. There's another tutorial I've got on mutability, if that's a little confusing, but basically, and also in the manipulating classes tutorial that's covered, but basically, yeah, I can set the radius over here of that round widget there. So there we go, it's casting back to round widget in order to access that method. There's a very important point to observe about casting. Casting only tells the compiler to treat a type as another type. It doesn't actually change the underlying type. So here we have a round widget that's being implicitly converted via an upcast to I widget, but that's only saying treat this round widget as an I widget. It's still underneath a round widget, and the cast won't be successful unless we retrieve one that's actually a round widget. This also leads to an observation about application complexity. Once everything's an I widget, it's more confusing for you and people reading the code to know what was originally a round widget. So there can be a case where you want to store everything only in a collection as an I widget, but if you've got another way to directly access the original round widget instance, because classes can be in multiple collections, the same instance, that might be a better way to do it. And it's also worth discussing performance at this point. So all the conversions use some kind of performance, even the implicit conversion, there's some kind of instructions there in the CPU. The explicit conversion is also doing literally this type check. There's some kind of internal thing going on where it's saying, can this be this? So that uses a bit more performance. That being said, don't get in the mindset that casting uses performance, though I should never do it. Your computer can do a lot of type conversion, and particularly for something where it's like going to do some type check every time the user clicks on something, that's probably fine. If it's like a tight loop, thousands and thousands of times a second, then maybe you want to find a structure that avoids casting. Last important point before we move on is about errors. So explicit downcasting is more error prone, as in literally there is a whole class of exceptions, type mismatch you can get with downcasting. The reason you can't get them with upcasting, and why upcasting is safe and implicit, is that the more general type, the draw by iWidget, it should be guaranteed, if we've implemented these definitions properly, that these can always do what iWidget can do. Same with the inheritance pattern. Every child should be able to do everything a parent can do. But not every parent can do everything a child can do. Not every general type can do everything the more specialized type can do. Therefore, there's the potential for errors here. CastAs avoids those by doing a check, and hopefully you only run the downstream code when the check is successful. The way potential error states are handled is one of the differences between the different ways to cast things. For example, there's another node called Hardcast, and this one specifically gives you an error if things are wrong. So currently we're getting the round widget, that's all fine, but if I try and retrieve the rect widget, we get an exception, invalid cast. We throw around the word object a lot in programming. Object has yet another meaning. It is also the base type of every single type in C#, including anything we patch or create in v4. So object is the parent and everything inherits from object. This means anything can be upcast object. So if we look here, we have a spread of round widget and rec widget, but also a bunch of other random stuff, audio stream, GUID, IP address, all of those can be connected to a spread of object. And you can see it's automatically upcasting them in the singular context to object here. We have a spread of object. And then we can get those and try to do some casting. I think I need to reset this for that to work. There we go. 0 is definitely a round widget, gets that. 1's a rect widget, gets that. 2 is not a rec widget, it's an audio stream. They don't succeed to cast. Now, I think you can see how doing this could lead to a fairly confusing application, could lead to runtime errors, all sorts of stuff where you've cast a bunch of things to object and then the application's so complex it's not totally clear what's what by the time it gets downcast again, and either you've got to rely on a lot of checks of casting or risk some runtime errors or something like that. So this is not ideal for this case. If round widget and rec widget, for example, should be in a single category, then yeah, interface is perfect for this. Make them a spread of iWidgets, and that should be a much clearer application. The object type does have some very specific use cases, things only it can really do. It's kind of like a runtime version of generic, but even in the runtime, it says this type could be anything. And sometimes indicating that is useful, That's literally how the CastAs node works. If we copy it here, the input is object, so it says at runtime that could be anything. The output is generic. It says by compile time we'll know exactly what that is, and that's what downcasting is. We're going to take specifically an object that could be anything and downcast it to something specific at runtime. Generally, in the v-for context, I would avoid typing to object. There's maybe a few use cases where that's the best way, some really advanced library development or stuff to do with reflection and serialization. But otherwise, if it can be avoided, if you can just have a few different variations explained well through help patches and stuff, I think that's going to result in less confusing code. That being said, these tools are here to be used. By all means, experiment with it, have fun. You're all smart people. I think you'll get it. The main thing is be safe, and we'll talk about that a bit more with the explicit downcasting. With this one, we use if gates to make sure we don't get type mismatch errors. Let's look at a few of the other ways we can explicitly downcast. Okay, there's another handy way to do a little bit of downcasting here. When you have a spread, and in this case, we've set up another spread of iWidget made of roundWidget and rectWidget. We have a node OfType sequence. Sequence will operate on spreads, of course. And what it does is it's doing something like a CastAs on every item in the collection, and then the ones that pass, it keeps. Therefore, the result is, if we look up here, we have 1, 2, 3, 4 rect widgets. We run OfType on that sequence, and it only returns the 4 rect widgets. Over here, we've got OfType, and I'll show you when I create this, actually. It's generic on the bottom. It's not going to do anything until it's connected to the downstream type. So from the downstream type, the OfType gets its type, and it says, okay, only things that are round widget will get passed through. Kept. Kept is not a word, but kept is a word. So the round widgets get kept, the rect widgets get kept over here. This also provides a level of safety, the same as the CastAs. You put an if region, it only executes. This will return an empty collection if nothing matches, therefore nothing downstream will execute. So yeah, there's a safety feature there as well. Let's also look at OfType Reactive. This one operates on observable message streams and does very similar filtering to the one we saw with sequence. It only lets through ones that pass the downstream type. And in fact, if I delete that, you'll see it's not typed until it can work out its type from what's downstream. And then it says, oh yeah, I'll only pass round widgets. If I click on that, yeah, round widget's received. And if I click on that to send a rect widget is received. Beautiful. In terms of performance, these OfTypes in the sequence and OfType Reactive are doing type checking on every item in the sequence or every message that arrives. That does cost a little bit of performance, but probably not dramatic in most use cases. And then we have Typeswitch. Typeswitch has a very specific use case. It maybe looks a little more flexible than it is at first glance. So the use case is at runtime, take a limited range of defined types and convert to a specific type. And we're going to do a patch along here because the UX is a bit weird with Typeswitch. So first, let's make a Typeswitch with advanced aspect on. Typeswitch 3 we're going to use, and we'll go region stateless, so this supports 3 types. All the code inside a Typeswitch region must be typed. It doesn't support generics inside it, so you can't do a thing where it's like, oh yeah, I want to use the generic definition, but then extend it with a couple more types. I'll show you what I mean. If I do a toString in here, then it's generic, but I'll need to connect it to one of these to run. This pin can't be generic. There's no switch to make the type switch itself generic. I have to give this a type. In this case, I'm going to say just good old float and connect that. And then we're also going to do, let's just say what we want is a string. So if we get a string, you should just pass that through. And if you get an integer, you're also going to convert it to string. And note it wasn't running until all of those had a type also. And this is what I mean about the UX. So note that doesn't appear to connect straight away. What I've got to do is assign this to match function 3 in order to be able to connect it to that color pin. Then Typeswitch takes object type only. So we've got to convert to object. If we just had a singular thing here and we were only using this instance of Typeswitch, if I just put a float here, then that will connect there, of course, and I'll get a result of the float as a string. However, more practically, you're going to want to use this in, say, a for each loop, and then we have a spread of things. Let's add a spread and connect these together. 3 items. And we're going to connect that here. So now that'll give us a spread of object. One of these times we have to mess with the object type. And let's put an integer on this one and a string on this one. I had to force that because it went to type integer, so I had to hold space. Now it's saying I comparable. Oh, it's found another way, a common type. And if I go float here, oh, there's still I comparable. Okay, the compiler's done something clever here, but ultimately by the time they get here, they're still object. Doesn't really help us. And if we go result out of here, then we should have, yes, 3 strings, 45, text, and 0. To be clear, what Typeswitch does functionally is similar to a bunch of CastAs connected to if blocks. I don't know if it somehow does it faster via some magic, but basically, functionally, it's like it tries to cast as the first thing, and if that cast is successful, executes the code to convert it to the specific type you want. If that cast wasn't successful, then it tries again for the next type, and if that cast wasn't successful, tries again for the next type. So you can also achieve that same behavior of Typeswitch with a chain of if blocks and casts. All right, we're almost at the end. We need to talk about collections and collection-related-y things. So I've got a question for you. If A implicitly converts to B, does collection A implicitly convert to collection B? And the answer is maybe. Isn't that an annoying answer? But there's some details here. There's stuff called variance and contravariance and things. It's actually super complicated and a bit annoying. But for us, I think I'll just break it down to what it means for us practically. So yes, direct implicit conversion is possible for some cases. Most of the .NET collection types, you can go from subtype to supertype. So you remember round widget is the subtype of iWidget because of their interface, because round widget implements the interface iWidget. So you can just connect those directly. And the same with observable round widget and observable iWidget. That's very handy that observables will automatically upcast like that. However, direct implicit conversion is not possible with some other cases. Spreads, so it works for sequence, but it doesn't work for spread. In this case, you'll need to do it in the singular context. We'll talk about that. It also does not work for any of the numeric implicit conversions back from the start of this video. Only works for reference types, not value types. Again, it's a language limitation. C# language limitation, I should say. So the workaround when this implicit conversion isn't working in the collection context is just do it in the singular context where we know it works. A for each loop will get you out of trouble here, and then our round widgets can become iWidgets for the spread, and then same for the sequence numeric types. What you've got to watch out for, and this is where it can get very confusing, is that the compiler does find a way. And in fact, you've already seen this. We've got round widget and rec widget together in a spread, and we just said spreads don't support this kind of variance. However, round widget and rec widget are actually here being converted in the singular context. The compiler worked out that iWidget was going to be the common type of these two, and so there we have rec widget into iWidget, round widget into iWidget, and there we are. We have a spread of iWidget. More confusing when you get something like this. Again, we just said it doesn't support merging spreads. So how can we have a concat that's taking a spread of round widget and a spread of rec widget and going to a spread of iWidget? In this case, there's a double level of confusion going on. So what's happening is this is concat sequence, and spread happens to be the spread, the collection type, not the inner type round widget. Spread happens to implement sequence, because sequence is actually I enumerable. So spread implements sequence. Spread then converts to sequence, so then that can become a sequence of round widget, and sequence does directly convert. You remember up here, sequence round widget does directly convert to iWidget. So this is a double implicit conversion. That goes from spread round widget directly to sequence iWidget there, and then it can mash two, same thing happens here, it can mash two sequence iWidgets together to give us sequence iWidget. Oh no, and then what this string does is output a spread, and then internally it upgrades it to a spread. There you go, last bit, and we get a spread iWidget out. So got to watch out for those things that can be confusing if you weren't expecting an upcast to work, or you see that works and then you get confused about the kinds of variants that are possible. That brings us to the end of the type flexibility tutorial. Thank you so much for watching. Hooly dooly, I hope you had as much joy as I've had making this. That joy comes from empowering you to tell the machine exactly what you want it to do with types or pretending things are different types, all this kind of fun. So I hope you go out there and make really advanced programs or look at this stuff and say, now I'm going to simplify things, actually. Either way, I hope you're empowered to do it. Make some cool stuff. Enjoy.